Hello everybody, welcome back for today's lecture on material balances for combustion reactions. In the last lecture we looked at some of the terminologies associated with combustion reactions and we understood the fundamentals associated with combustion reactions. So, these reactions are important for industries because they help in producing energy. So, now we will be performing material balance calculations that are done for combustion reactive processes. So, here is the first example. A hydrocarbon gas is burned with air. The dry basis product which is formed is 1.5% carbon monoxide, 6% carbon dioxide, 8.2% oxygen and 84.3% nitrogen. There is no atomic oxygen in the fuel. Calculate the ratio of hydrogen to carbon in the fuel gas and speculate what the fuel might be. Then calculate the percent excess of air that is being fed to the system. So, here you are asked to calculate the carbon to hydrogen ratio, which would help us in identifying what fuel has actually been used. So, let us see how we can solve this problem. Just like any other material balance problem, we will start with assuming a basis. Here the composition of the product gas is known. So, this is the dry basis. So, based on that we will use the basis for the product gas on a dry basis. So, the basis would be 100 moles of dry product gas. So, the flow chart for this system can be written as you have a product stream which contains 100 moles of gas and this gas contains 1.5% carbon monoxide, 6% carbon dioxide, 8.2% oxygen and 84.3% nitrogen. So, in addition to this you would also have water vapor which is leaving the system. So, the dry gas contains these components and in the actual product gas which contains water vapor we will assume that there is water as NW moles of water which is leaving the system. So, you would have two inputs, one being the fuel and the other being air which is supplied for burning the fuel. So, the fuel would contain N moles of Nc moles of carbon and NH moles of hydrogen. So, it has been mentioned that it is a hydrocarbon gas and it does not contain any oxygen in the fuel gas, which means you have only carbon and hydrogen which have been represented here. So, you have air which is supplied as Na moles of air. So, this would contain 0.21 moles of oxygen per mole and 0.79 moles of nitrogen per mole. So, now with all this information we now need to calculate how much of water is leaving the system and what is the ratio of Nc to NH and what is Na, so that we can identify the percent excess of air which is being supplied. So, how do we go about performing these calculations? The first simple balance equation we can write would be the nitrogen balance. When we write the nitrogen balance, what happens is it is 0.79 times Na, which is the number of moles of air, will be equal to 0.843 times 100. As nitrogen is considered to be an inert component and as the process is at steady state, you would not have generation or consumption terms for nitrogen and accumulation would also be 0. So, this means input equals output, which is what I have written down. So, based on this you can calculate the number of moles of air entering the system as 106.7 moles of air. So, the next step is to calculate the ratio of carbon to hydrogen. How do we go about doing that? What balances can we write? To calculate the ratio of carbon to hydrogen, we will be writing atomic balances for carbon, hydrogen and oxygen. Using this we will be able to calculate the number of atoms of carbon which is entering and number of atoms of hydrogen which is entering, from which we can calculate the ratio of carbon to hydrogen. Let us start with the carbon balance. So, the carbon balance would be input equals output, at steady state accumulation is 0 and atoms cannot be created or destroyed. So, generation and consumption terms are 0. So, giving us input equals output. Input is Nc, we have assumed Nc is the number of moles of carbon atoms which is entering, and carbon atoms are leaving the system in the form of carbon monoxide and carbon dioxide. So, you have 100 moles of dry gas times 0.015, which is the mole fraction of carbon monoxide in the dry gas, times 1, which is the number of atoms of carbon present in carbon monoxide. This plus 100 times 0.06 times 1, which is the amount of carbon atoms leaving in the form of carbon dioxide. So, solving this we get 7.5 moles of carbon is present in the input fuel gas. Now, writing a balance equation for oxygen, we would have 0.21 times Na, which is the number of moles of air which is entering, times 2, because oxygen enters as molecular oxygen which contains 2 atoms of oxygen per molecule of oxygen present in air. This equals Nw times 1, where Nw is the number of moles of water vapor leaving the system and containing 1 atom of oxygen. So, similarly we have product gas which is 100 moles containing oxygen in the form of carbon monoxide, carbon dioxide and oxygen. So, you have 0.015 times 1 atom for carbon monoxide plus 0.06 times 2 representing carbon dioxide plus 0.082 times 2 representing the oxygen molecule. In this particular equation we already know the value of Na. So, from here we can calculate the value of Nw as 14.9 moles, which is the number of moles of water which is leaving the system in the form of water vapor. To calculate the number of atoms of hydrogen which is entering into the system, we would have to write an atomic balance for hydrogen. The hydrogen balance would be NH, which is the number of moles of hydrogen entering in the form of fuel gas, would be equal to the number of atoms of hydrogen leaving the system, which would be only through water vapor. So, that would be 2 times Nw. As we already calculated Nw as 14.9, we can identify NH as 29.8 moles of hydrogen. So, this implies the ratio of hydrogen to carbon is NH divided by Nc would be 29.8 divided by 7.5. This comes out to be 3.97 moles of hydrogen per mole of carbon. With the ratio of carbon to hydrogen being 1:4 roughly, we can assume that the fuel gas which has been used would be CH4, which is methane. Now that we have the information regarding the fuel gas which is being fed, the next part of the problem asks us to calculate the percentage excess of air. So, for performing this calculation, we first need to identify what would be the complete combustion reaction for the fuel gas which is used. So, the fuel gas we have identified to be methane. So, which means methane plus oxygen should form carbon dioxide plus water vapor. So, this reaction when balanced would be 2 atoms of oxygen, so 2 molecules of oxygen reacting with 1 molecule of methane would form 1 molecule of carbon dioxide and 2 molecules of water. So, this would be a balanced reaction. You have 1 atom of carbon and 1 atom of carbon in both sides, 4 atoms of hydrogen and 4 atoms of hydrogen and 4 atoms of oxygen and 4 atoms of oxygen on both sides. So, this means 1 mole of methane requires 2 moles of oxygen for complete combustion. From the calculations we have done, we know that 7.5 moles of carbon is entering, which means 7.5 moles of methane is also entering into the system. So, for 7.5 moles of methane, you require 15 moles of oxygen. So, this means moles of air required would be equal to 15 divided by 0.21, which is 71.43 moles. So, you need 71.43 moles of air that needs to be fed for complete combustion of 7.5 moles of methane gas which is being fed. So, to calculate percentage excess air, we basically calculate the amount of air which is fed, which is 106.7 minus amount of air which is required, which is 71.43, divided by the amount of air which is required, 71.43 times 100. This gives us the percentage excess as 49.4%. So, 49.4% excess gas has been supplied for this reaction. So, with this we have calculated all the values that have been requested for in the problem. Let us move on to the next problem and perform material balances for a new system. This example problem states that ethane is burnt with 50% excess air. The percentage conversion of ethane is 90%, and amongst the ethane which is burnt, 25% reacts to form carbon monoxide and the rest reacts to form carbon dioxide. Calculate the molar composition of the flue gas on a dry basis and the mole ratio of water per dry flue gas. So, this problem gives us a partial combustion reaction. That is why you have both carbon monoxide and carbon dioxide forming. So, ethane is the fuel gas. So, we now need to write two different equations, one for complete combustion and the other for partial combustion producing carbon monoxide. Let us write both these equations. Ethane is C2H6 reacting with oxygen to form carbon dioxide and water vapor would be the complete combustion reaction. Ethane plus oxygen forming carbon monoxide and water vapor would be the partial combustion reaction. Now, let us balance these two equations. So, we have two atoms of carbon, so this becomes 2, and to balance hydrogen we add a 3 here. So, finally, to balance oxygen it would be 7 by 2, and similarly 2, 3 and you have 5 by 2. So, these are the two balanced equations for the partial and complete combustion reactions. So, the problem statement tells us that we have ethane which is entering, C2H6 which is entering, and you have excess air, 50% excess air is being fed, and the product obviously contains both the partial and final combustion complete combustion products. In addition, you also have unreacted ethane because you only have 90% conversion of ethane. So, some of the ethane which is coming in is leaving the system without being combusted. So, this would mean the final composition of the product gas would be N1 moles of ethane, N2 moles of oxygen, N3 moles of nitrogen, N4 moles of carbon monoxide, N5 moles of carbon dioxide and N6 moles of water vapor, with all these leaving the system. For performing calculations, we will assume a basis of 100 moles of ethane which is being fed to the system. So, this would be 100 moles. So, the basis we have used is 100 moles of ethane. Let us go about performing these calculations. First thing we need to do is identify how much air is being fed. We have been told that 50% excess air is fed. So, based on that we can calculate how much additional air has been fed. So, using the stoichiometry we can calculate the theoretical amount of air which is required. Theoretical air required would be for 100 moles of methane, sorry 100 moles of ethane, you have to calculate theoretical air which is required, we will have to assume complete combustion. So, for every mole of ethane which is fed, you need to have 3.5 moles of oxygen for complete combustion to occur. So, the theoretical air requirement would be based on theoretical oxygen, which is 3.5 moles of oxygen per mole of ethane. So, theoretical moles of air would be equal to 100 moles of ethane times 3.5 moles of oxygen per mole of ethane times 1 mole of air per 0.21 moles of oxygen. This would give us the number of moles of air which is required. So, to calculate the amount of air which is supplied, we would multiply this by 1.5 times theoretical air calculations. So, the amount of air which is actually supplied would be 2500 moles of air. We also have been told that 90% of ethane is consumed in the conversion. So, that means 10% is remaining and it will be leaving the system as unused reactant. So, unreacted ethane would be 0.1 times 100, which is 10 moles of ethane. So, this is the unreacted ethane. So, the rest 90 moles has been consumed in the process. Now, let us start with the material balance problems. So, let us start for ethane. So, ethane is actually taking part in the reaction, however, it is only being consumed, you do not have any generation of ethane. So, your output would be equal to input minus consumption. So, input here is 100 moles based on the basis we used and consumption we just said was 100. So, output of ethane which we which we wrote down as N1 would be equal to 10 moles. So, if we were to use the other information which has been given, that is 25% of the ethane that is consumed actually goes into carbon monoxide and the rest goes into carbon dioxide, we will be able to calculate how much of ethane went into carbon monoxide reaction and how much went into carbon dioxide reaction. So, if we were to write a balance equation for carbon monoxide, it would be output equals generation, and the generation would be based on the stoichiometry of partial combustion. We know that 1 mole of C2H6 produces 2 moles of carbon monoxide. So, this means the amount of ethane which is consumed for this reaction times 2 would be the amount of carbon monoxide generated. So, we know that 90 moles of ethane is consumed. This implies 0.25 times 90 moles is consumed in is combusted partially. So, this implies you have 0.25 times 2 times 90 moles of CO generated. So, the number of moles of CO in the output, which is N4, would be equal to 0.25 times 90 times 2, which is 45 moles. The problem statement says that 25% of the gas consumed, ethane gas consumed, goes into forming CO, the rest actually goes into forming CO2, which means 75% of 90 moles which is consumed would go into formation of CO2. So, ethane that is completely combusted complete combustion would be equal to 0.75 times 90. So, based on the stoichiometry, we know that 1 mole of ethane produces 2 moles of carbon dioxide. So, this means carbon dioxide generated would be equal to 0.75 times 90 times 2, which would be 135 moles of carbon dioxide. When we write the balance equation for carbon dioxide, output would be equal to generation, because you do not have an input or consumption term, and accumulation is 0 for steady state processes. So, your output, which is N5, would be equal to 135 moles of carbon dioxide. So, the next aspect we need to look at is calculating the number of moles of water vapor which is produced. So, based on the stoichiometry, for complete combustion, 1 mole of ethane produces 3 moles of water vapor. So, what you have is next aspect to calculate is the number of moles of water vapor produced during these combustion reactions. Based on the stoichiometry for complete combustion, you have 1 mole of ethane reacting to form 3 moles of water, and similarly for partial combustion you still have 1 mole of ethane forming 3 moles of water vapor. So, this means for every mole of ethane which is consumed, you would have 3 moles of water vapor produced. So, we know that 90 moles of ethane is consumed, which would produce 90 times 3 moles of water vapor. So, again water balance would be output equals generation, giving output as N6 equals 270 moles. So, with this we have calculated the number of moles of most of the components. We still need to calculate the number of moles of nitrogen and oxygen. So, nitrogen is a non-reactive component. So, whatever nitrogen is entering would be leaving the system. So, nitrogen is input equals output. So, input is moles of air times 0.79, which would be the number of moles which is leaving the system, N3. So, N3 equals 0.79 times 2500, giving you N3 as 1975 moles. So, the only final thing which needs to be calculated is the number of moles of oxygen which is leaving the system. So, for performing those balances for oxygen, we would have oxygen which is coming in and oxygen leaving and oxygen being consumed. There is no oxygen generated in the process and accumulated in the process. So, oxygen output would be input minus consumption. Input for oxygen is 0.21 times 2500 moles of air. Consumption of oxygen would be calculated based on the stoichiometry. So, if you look at the stoichiometry for complete combustion, you have 1 mole of C2H6 reacting with 3.5 moles of oxygen. For partial combustion, you have 1 mole of C2H6 reacting with 2.5 moles of oxygen. So, based on the number of atoms, number of moles of ethane going into complete combustion and partial combustion, we can calculate the number of moles of oxygen which has been consumed. So, we know that 0.25 times 90 moles of ethane went into partial combustion, which means 0.25 times 90 times 2.5 moles of oxygen was consumed in the partial combustion reaction. In the complete combustion reaction, we have 0.75 times 90 moles of C2H6 taking part, implying 0.75 times 90 times 3.5 moles of oxygen being consumed. So, output would equal to input, which is 0.21 times 2500 minus the two consumptions, which is 0.25 times 90 times 2.5 minus 0.75 times 90 times 3.5, giving a value for the output, which is N2 as 232 moles of oxygen. With this, we have calculated the number of moles of each of the component which is present in the product gas which is formed. We also need to calculate the molar composition of the flue gas on dry basis and the mole ratio of water to dry flue gas. So, this can be done basically by calculating the total number of moles, ignoring the moles of water which would be the dry basis. Let us try and do this for the next part. Now that we have the number of moles for each of the components, we will have to calculate the molar composition of the flue gas on a dry basis. So, let us do that. So, what we have done here is we have written down the number of moles of each component except water. As we wanted to calculate the dry basis, we have written the number of moles of ethane, which is 10, number of moles of oxygen, which is 232, number of moles of nitrogen, which is 1975, number of moles of carbon dioxide, which is 135, and number of moles of carbon monoxide, which is 45. The summation of all these components gives us a total number of moles as 2397. So, the mole fraction for each of these components would be 10 divided by the total number, which is 2397, giving you a mole fraction of 0.0034, and for oxygen it would be 232 divided by 2397, which is 0.0968, and for nitrogen it will be 1975 divided by 2397, giving a value of 0.8239, and carbon monoxide mole fraction would be 0.0188, and carbon dioxide mole fraction would be 0.0563. Now that we have calculated the composition of flue gas based on the dry basis, we now need to calculate the mole ratio of water to dry flue gas. We know that the total number of moles of dry gas is 2397, and we also know the number of moles of water. So, moles of water was calculated as 270, moles of dry flue gas is 2397. So, the ratio is 270 divided by 2397, giving you a value of 0.1126. With this, we have performed material balance calculations for a combustion reaction where ethane was burnt with 50% excess air. Now that we have performed these two example problems for material balances, we have a reasonable introduction towards performing such material balance calculations in processes where combustion reactions are taking place. Thank you.